Hi there, and welcome to Chapter 2.6 from Stevens' Matrices, Vectors, and 3D Math. In this chapter, we're going to talk about planes, not the flying machine, but the two-dimensional objects as pictured there. I'm going to break this up into two videos. It's not really a long chapter, but it's worth taking a break part way through. So this is the first one, and we will get started right after I get this into full screen mode. Alright, there we go. So planes. And again, this is just a two-dimensional plane within 3 space, right? And so we're going to define a plane within 3D. And really all we're going to need to do this is a point, we call it P, x1, y1, z1, such as right there, that's the point, and a normal vector. And that normal vector is orthogonal or perpendicular to all vectors in the plane, right? It'll be 90 degrees with every one of these vectors, right? Okay, and so that's what I call N, and it has components X or A, B, and C. All right. All right. So if that's our definition, right? We have a point on the plane and a normal vector. Then any vector in the plane has to be at a right angle with that normal vector, or orthogonal, and the definition of orthogonal is that the dot product is 0. So if you create this vector, all right, PQ, I try to create PQ, that's easy enough to do, just because PQ is going to be essentially Q minus P, so it's going to be X minus X1, Y minus Y1, and Z minus Z1, right? And if that's going to be orthogonal to N, right, if I need this right angle here, then the dot product of PQ and N is going to have to equal 0, right? And so that's what's going on down here. N dot PQ equals 0. And if you write all that out, N, remember that just has the A, B, C right here and up here. And if I dot that with PQ, I'm going to have A times X minus X1 plus B times Y minus Y1 plus C times Z minus Z1. We're going to require that that equals 0. And so if you distribute all of those components from the normal, if you distribute the A across here, the B across here, the C across here, and combine those into one constant that we call D, specifically D is all this stuff here, and then we get all of the variables X, Y, and Z in this first part. And so this form right here is the general equation, right? And it's similar to the standard equation, it's just after you simplify and collect all the constants. You can put it in functional form, provided C is non-zero. You can write it like this. In this case, Z is a function of X and Y. If C equals 0, you obviously can't do that, so you can maybe shoot for functional form in terms of Y as a function of X and Z, or if that doesn't work, X is a function of Y and Z. But the standard form we will use will be right here. And sometimes we'll even take that D and swing it over to the right-hand side. Okay, let's do an example. If, for example, you're given a point and a normal vector, that's sort of what you want, that's the ideal situation. Find the general equation for that plane. And we'll say this is the point, 1, negative 2, 3, and the normal vector is 4, 5, negative 6. Then you just take 4 times x minus 1 plus 5 times y minus negative 2 minus 6 times z minus 3, and set that equal to 0 as I did right here. Right? And then the next step is just to distribute the 4, the 5, and the -6 gets you here to this intermediate step. Collect all your constants, and you get this final form: 4x plus 5y minus 6z plus 24 equals 0. So this is what an equation for a plane looks like. All right. It's sort of the three-dimensional analogy to a line. All right. And a line in 2D is ax plus by plus c equals 0. Sometimes you'll see it ax plus by equals c, one of those. But this is, so this is a line in 2D. And then if you just go up one dimension, what you get is the equation or plane in 3D. All right. So what you might learn in geometry is that 3 points determine a plane, right? That's why a stool never wobbles. So if we're given 3 points, how do we find the plane through those 3 points? Well, I'm going to show you one way here through this example. Suppose my 3 points are P, Q, and R. What I want to do, so if this is my plane right here, I want to find the normal vector, right? And so to do that, what I'm going to do is, if this is, say this is P and this is Q and this is R, I'm going to create these two vectors, PQ and PR. Right, PQ, and then over here will be PR. And if I take their cross product, the result is going to be orthogonal to both of those vectors. In other words, that's going to be the normal vector to my plane. So I first define PQ, that's just Q minus P. Then I define PR, which is just R minus P. Then I want to find the cross product. Never all that much fun, but not too bad if you just remember the determinant of this matrix. So it's I times the determinant of this matrix minus J times the determinant of the matrix that's left when you cross out that row and that column plus K times the determinant of that matrix. And when you do that out, you get a normal vector 9i plus 6j plus 12k, or 9, 6, 12. So that's my normal vector. And I can use any of my points. I have a P, Q, and R. I'll use P. So using this for N, all right, and this for P, I'm going to get my standard equation for the plane by taking 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1. Set that equal to 0 right here. Combine my constants, or distribute my constants, 9x minus 18 and so forth. And when you combine them into one constant, you get this general equation. If you had used a different point, say Q, and followed the exact same procedure, you would get the same equation for the line. And if you used R instead of that, you would also get the same equation for for this plane. But the point that's worth making is that you get the same plane. In this case, the equations are identical. But if you wanted to, you could take this equation for this plane and multiply by 1/3 or divide by 3 all the way across. And what you get is 3x plus 2y plus 6z minus 12 equals 0. So notice, just like for the equation for a line, it's not entirely unique. There's factors that you could throw in or take out. There is a unique way of defining it, but I'm not going to get into it. It isn't that important to get it into its unique identifying form. Here's another example. Suppose I have this plane that goes through this point. So I have a point, and it is perpendicular to this line. All right? So that's my point, and it is perpendicular to this line. How do I find that plane? Well, it's actually easier than you would think, right? You don't have to do too many calculations because the information you need is actually staring right at you. If you take a look at this line, right, and maybe here's a little picture. So I have a plane, and I have a line that needs to go through that plane, and that line is going to be perpendicular to the plane, right? But this line has a direction vector. We called that direction vector v in the past, right? And that direction vector is found by getting the coefficients of t in my line, all right? So the direction vector here is just -1, 0, 3. So that's the direction vector for the line, but that's just going to be the normal to the plane. All right? So that's all I use. I use this point and this normal vector, and so I get -1 times x minus 2 plus 0 times y minus 1 plus 3 times z minus -4. That gives me this equation, the standard equation. I distribute my constants, combine my constant terms together, and I get this for my equation for the plane. All right? And it is sort of worth pointing out that this, if you notice this thing, it's a little strange. This direction vector, all right, is actually parallel to the YZ plane. But the important thing to notice, if you do x, say, y, z, and we'll get into drawing these in a second, is that this plane looks something like this. All right? There is no y-intercept. It's actually parallel to the y-axis. Try to picture that in your head. The y-axis is going back into the page here, and this plane is parallel to that, so it never actually hits the y-axis. Right? And it makes that a little easier to comprehend. We're going to do a little sketching. Right? So how do you sketch these things by hand? Sketching a plane. And the way you start with this, and it doesn't always work. It turns out that your intercepts are not always on the positive axes. It does make it easier to sketch if they are. But you generally start off by doing x, y, z, and then you just want to find out where the intercepts are. You connect it with the triangle, and that gives you a decent little picture of what the plane looks like. All right, so here's an example. I have this plane right here. What does it look like if you were to try to sketch it? Well, the game to sketching these things is all about intercepts, right? So if I want the x-intercept, and then if you look at the x-intercept right there, or anywhere along this line, that is where y equals 0 and z equals 0. So if you want the x-intercept, you set y and z equal to 0. And if you set y and z equal to 0 here, you just have 4x minus 12 equals 0. And if you solve that, you just, quite simple, 4x equals 12, x equals 3. And so that's how I got that point on my graph, right? So x equals 3, that's the x-intercept. If you want the y and z-intercept, you go through the same process. Only when you're looking for the y-intercept, you set x and z to 0. Setting x and z to 0, that makes that go away, that go away. And you have 2y minus 12 equals 0, which gives you y equals 6, so you get 6. Remember, the positive y-axis is set into the page in this orientation. And likewise, if you want the z-intercept, you set x and y to 0, solve that equation, and you get z equals 6. So once you have your 3 points, you just draw your triangle connecting them, and it gives you sort of an idea of where this plane resides in 3 space. It isn't always that easy. Sometimes, especially when one of the planes is parallel to one of the axes and you don't get 3 intercepts, or if you get negative intercepts. But it helps picture it in your head, and as you're moving around in 3 space, it's nice to just sort of practice this stuff. Okay, let me do one more little thing, and then we'll take a break before the next video. So Here we're going to look at the angle between two planes. Suppose I have two planes as pictured here. If I want the angle between them, I'm basically looking to get the angle between the two normal vectors. So if I have one normal vector here and another normal vector here, if I get the angle between them, that's the angle we're talking about, right? And specifically, if you look at these two planes, there's this angle here, and then there's this angle here. So in order to do that, this was the formula for the angle between two vectors, only it didn't have this absolute value. These absolute value signs weren't there. By sticking the absolute value signs in there, we assure ourselves that we're getting the acute angle. We're always getting the smaller of the two angles when two planes intersect, right? Because when two planes intersect, I'm going to get two different angles of intersection. So this absolute value on the top ensures that I'm finding the smaller one, right? Or the one that has a positive dot product. And so once I get this, then in order to get the actual angle, I have to take the arc cosine of my right-hand side, and that gives me the angle. And the planes are perpendicular if their normal vectors are perpendicular. And the planes are parallel if their normal vectors are parallel, or in other words, their normal vectors are scalar multiples of each other. Alright, so if I want to find the angle of intersection between this plane and this plane, it's really quite easy. I go to this formula, and you need the two normals, but the normals, and this is an important thing about planes, the normal vector is staring right at you if you look at the right place. Like the normal vector for this plane right here is comprised of 3, -1, 2. So that's the first one. It's comprised of the coefficients of x, y, and z in the equation for the plane. And then the normal vector here is just 1, -2. And if you look at this, there's not negative. The -2 is in front of the z. There is no y term, so the y actually has a 0 in front of it because you can't see it. But the 1 for x, and then the -2 for the z. And there's my normal vector. So then to get the angle between the two planes, you just take the two vectors and get the angle between them. But when you take n1 dot n2, so that's 3 times 1 plus -1 times 0 plus -2 or 2 times -2. So really what you get there is 3 minus 4, which is -1. So n1 dot n2 equals -1. But we're going to take the absolute value of that, which is why we have a positive 1 there. Divide by the size of n1, size of n2, and so this gives you the cosine of theta, the cosine of the smaller of the two angles between the two planes, and that gives you 1.45 radians. And you just use either a calculator or, in this case, MATLAB with the a cos 1 over root 70. All right. And if you convert those radians to degrees, you get 83. And this angle will always be less than or equal to 90 because you're getting the smaller of the two. Okay, so in the next video, we'll get into getting the line of intersection of two planes. And as you can see, when you intersect two planes, you actually get a line of intersection. And so in the next video, we'll start with determining what that line is. But I think for right now, we're going to take a break, and I'll see you at the next video.